Prima, you pretty much ready to go?
Does the pointer work?
So I think jurors are all in place, teams are all in place for the final stage of the 5th round of IYPT 2025. And I'm really looking forward to the Thai report on sound versus fire. So let's start the clock and enjoy.
Okay. Problem 12, sound versus fire. A small flame can be put out by sound. Investigate the parameters of the flame and characteristics of the sound that determine whether the flame will be extinguished. Now here are the flame parameters, the flame's height, and the sound parameters, the amplitude, frequency, and distance from the source. Now here's our outline. So as you can see here, when fire is exposed to sound, sound possesses the ability to be able to extinguish the fire. Now here's our experimental setup. So initially we have the speaker, and then the sound level meter, which controls the amplitude and the frequency of the sound, the microphone, which controls the decibel, and a hot wire anemometer that controls the speed of that measures the speed of the wind. Now we have the experimental setup for fire, in which initially we have a butane gas can, a gas lamp, a speaker, and as well as a camera. And through this, the fire's behavior was investigated. Now here's the initial of the fuel. Through this, we utilized a gas lamp because the candle has quite an inconsistent melting wax, which could cause instabilities. Therefore, we utilized a gas lamp in which it had more a constant gas feed, reducing error. So a cause of the fire extinguishment is oxygen, fuel, and heat, in which through this investigation, we noticed that we have an unlimited supply of oxygen, fuel, and however, we do not have an unlimited supply of heat. Therefore, the main reason why the fire extinguishes is due to the removal of heat. Now, let's go through the phenomenon explanation. Now, here we have a speaker with sound-induced wind. Now, as we all know, sound comes out as a longitudinal wave. Now, this longitudinal wave induces pressure waves. So the areas where it's less compressed would induce lower pressure, and the areas where it's more compressed would induce higher pressure. Now, through this, we are aware that sound comes out as a concentrated beam. Now, here is the oscillations of the particles. Oscillations of the particles near the z-axis would have more oscillation than the ones near the boundary layer. Therefore, when we know that when sound comes out, it oscillates, and if there's no viscosity, the particles and the oscillatories will oscillate in sync and at the same time. However, if the viscous term is introduced into this experiment, we would see that the particles are introduced lagging to the particles, therefore including an out of sync phase in which the particles do not move at the same time. Therefore, this induces vorticity. Now, vorticity then induces the net airflow from streaming. Now, this net airflow from streaming then, when exposed to the flame, causes forced convective cooling. Now, forced convective cooling then removes heat. So the net airflow streaming from the wind removes heat from the fire, therefore causing the fire to extinguish. Now through this, we modeled the sound waves using a Gaussian profile, meaning that the intensity in the middle of the radius, middle of the sound is the most intensity. And as you spread out, the intensity decreases. Now let's go through the fire extinguishment. I separated this phenomenon into 3 cases. Case 1, flame displacement. Case 2, lengthened extinguishment. Case 3, instant extinguishment. And as you can see in case 1, wind goes in and the net airflow from acoustic streaming causes forced convective cooling, meaning this removes heat from the fire. Now, as we know that the flame from the fire is caused from the rate of combustion between fuel and velocity. And we know that the forced convective cooling also causes a cooling rate. Therefore, at this state, when the flame has not extinguished yet, we know that the rate of cooling is a lot less than the rate of combustion. Now, if we move on to case 2, we can see that exponentially growing disturbances are starting to occur in this case. This is because as wind velocity increases, it introduces a velocity gradient which causes more viscous shear forces. Now, the same thing occurs in this phenomenon, in which forced convective cooling is introduced in this rate. And although it takes a long time to extinguish, this is because the rate of cooling gradually begins to overcome the rate of combustion, therefore leading to lengthened extinguishment. Now, in case 3, Now in case 3, instant extinguishment, the wind from the velocity, with the wind from the acoustic streaming causes abrupt forced convective cooling. Now this pulls heat away from the burner tip, so the fuel cannot reignite and accelerates the fuel vapor too far away from the burner tip. Also, the very intense streaming of air also makes the flame subtly deformed. Therefore, at this rate, we know that the rate from cooling, from the forced convective cooling, greatly exceeds the rate from combustion of the fire. Now go to our theoretical model. Now at our theoretical model, the sound, this is a speaker in which induces sound along its propagating axis. Now this sound can be modeled utilizing the pressure profile equation, in which the first term captures the beam divergence and the divergent stream of the beam, the second capturing the Gaussian profile, and the third capturing the dissipation of sound energy along its propagating axis, and the last calculating the model utilizing the cosine wave. Now this equation can be proven to be the solution through the basic equations, such as the standard fluid equations of continuity, and as well as the Navier-Stokes equation. And in this experiment, we utilize paraxial approximation, which is quite reasonable for a stream. Now, through our theoretical model, RNB is the flat top radius of the sound, in which we will later see in our theories. And the acoustic intensity, as we know, can be calculated from this equation. Now, utilizing the past equation from the past slide, we can calculate the acoustic intensity to be in this slide, to be this equation. And then from that, we can calculate the driving force of the streaming velocity, or the air caused by streaming. And then after that, through the utilization of the streaming equation and the second order modified pressure, we can result in the velocity profile from acoustic streaming. Now this is our own derivation. However, the full derivation is too long to show, therefore we included it within the appendix. Now, we predicted the velocity profile to be similar to a parabolic profile as seen here, in which in our experiment, it was shown to be true. Now, in this experiment, we assume the paraxial profile, in which we are seen to be true in these first 3 stages. However, as wind starts to become very turbulent, we can see that the flame no longer follows the paraxial approximation. As we can see, when wind starts to become very turbulent, the Kelvin-Helmholtz instability occurs. The Kelvin-Helmholtz instability is the very big difference in the velocity gradient, which introduces viscous shear forces, therefore causing the flame to curl up, and therefore not leaving room for the paraxial approximation of the parabolic profile, as seen here. And for our phenomenon explanation, we then calculated the streaming force from the acoustic streaming, and by utilizing the acoustic intensity equation, we can then further integrate the equation and multiply by R and find the wind streaming velocity. And as we know, if fire comes out, the density near the fire is much less than the density near the air, therefore inducing buoyancy force and vectoring the fuel upwards. Now, as you can see here, this is the mass transfer rate equation, which is quite well known. However, we utilize this equation to then find the rate of burning of the fire, the rate of combustion between the fuel and the oxygen. Later, as we know, forced convective cooling also occurs because heat is removed through forced convection. Therefore, we can take this equation and derive for the rate of cooling. Now, through our experimental results, initially we investigated a phase diagram. The red part would be the no extinguishment. The gray part would be the lengthened extinguishment, and the blue part would be the instant extinguishment, in which through this we observed that as the frequency increases, the decibel required to extinguish the fire increases as well. Now, later we can see the relationship between sound intensity and distance, in which this compares our theory and experiment, as utilizing this equation, which is the change in decibel over time. However, this term accounts for the Gaussian profile and the Gaussian intensity, as we explained, in which the intensity would be more near the middle of the speaker and less as it diverges it out. Now, from our equation that we found the acoustic streaming velocity, we know that by increasing the decibel, or the sound intensity, it increases the pressure as well, therefore increasing the wind speed and increasing the acoustic streaming velocity. Now, after that, we also done experiments to vary the flame amplitude. And here we varied the flame amplitude to be 1 centimeters, 3 centimeters, and 5 centimeters. And through this, we discovered that as seen in the 1 centimeter flames, it takes around 95 decibels to be able to occur instant extinguishment. However, in the 3 centimeters one, it is also similar in which 95 decibels is required to reach instant extinguishment. And this is the value for the 5 centimeter extinguishment, as seen in this graph. So as we can see, instant extinguishment occurs at a higher decibel because flame amplitude when higher, the flame height when higher, has more combustion rate, therefore making it harder for the cooling rate to exceed the combustion rate. Now through our conclusion. In our experiment, we observed the parameters in which is distance, sound level, frequency, and flame height. Flame height having the flame parameters. Through that, we investigated how the flame is extinguished utilizing acoustic streaming, convective cooling, and the Kelvin-Helmholtz instability. So acoustic streaming is the wind induced from the speaker, in which we have explained, and convective cooling is the wind that was induced from the speaker, helps remove heat from the fire, therefore helping causing extinguishment. After that, the Kelvin-Helmholtz instability is the difference of the very large distance in the velocity gradient that causes a very turbulent wind that causes the flame to instantly deform in shape, therefore not following our parabolic profile approximation. And after that, lastly, we derived for the combustion rate, the cooling rate, the streaming force, and the streaming velocity, in which this is all our own contribution. And if we wanted to see the full derivation, I will show in the appendix later on within the discussion. And this, as we know, for the fire to extinguish, the cooling rate must greatly exceed the combustion rate of the fire. So that is it for my presentation. And here's the bibliography. Thank you.
Thank you, reporter, for the insightful report. Firstly, could I ask how long your extinguishing time is? Could you give some values? How long did it take for the flame to extinguish?
For lengthened extinguishment or instant extinguishment?
Both.
Lengthened extinguishment usually takes around 0.2 seconds around that.
How about instant?
Instant, in like less than 0.2 seconds.
I see. So can you tell me, what do you define a flame to be?
I define a flame to be, as seen in the, I define a flame to be this. So basically what is seen visible to us.
So it's just a region of combusting gas, specifically.
Yes.
Okay. Does it ever assume so your flame to oscillate back and forth in front and behind the behind the Bunsen burner?
Yes.
Okay, sure. Do you have any theoretical predictions for any of your graphs?
Yes, as seen, we have a graph comparing the theory and experiment. And also we have a qualitative explanation of the velocity profile.
How about, do you have any theoretical predictions for when the flame can extinguish?
No, we do not have a theoretical prediction. However, we do have an experimental result.
I see. Could you show the slide, please? If I'm understanding you correctly, you've only presented the results for when it can extinguish, but you're not able to use your theory to predict when exactly it can extinguish.
We utilize our theory to find the wind velocity, which then shows us when the fire is able to be extinguished.
But do you have any theory overlaid on these plots?
No, we do not have a theory overlay on this part.
I see. So could you go to slide 25?
Yes.
Slide 25, please. So could you explain what is alpha in slide 25 here?
Okay, so alpha is the decaying rate.
So how about pi here, the capital pi?
Where, sorry?
How did you get your second order modified pressure?
Oh, we derived for it, in which we can later show in the discussion.
So what, for your Reynolds number, what is your characteristic length scale?
My characteristic length is the, for the speaker, it's this.
I think we can discuss that later. Have you verified your sound amplitude? As in, have you verified that it plays a monochromatic wave? Okay, thank you.
Size of ชาติไทยอันนั้นคือ experiment ใช่พี่โอไม่ได้รันซิงไม่เคยรันซิงถ้าไฮไซต์มันจะเห็นปะถ้ากดเข้าไปมันจะเห็นไหมโอเคก็โอเคขึ้น
Good afternoon, everyone. I'm Kablan from Team Singapore, and I'll be opposing problem number 12, sound versus fire. In summary for the report, they discuss the sound as wind pushing the flame away from the fuel as due to vortices induced and which causes extinguishing. They quantitatively modeled the sound with the Gaussian profile and fitted the flame as a paraxial fit. They experimentally varied parameters such as the flame height, frequency, and distance. For the report, they had a good experimental setup. They used a high-speed camera to track the motion to a high degree of to a high accuracy. They had a thermal camera to measure the temperature of the flame, and they used a function generator for the sound, amplitude, and frequency. They also used an anemometer for wind speed. Using all these methods, I think is quite good as they're able to they're able to get good data for the experiments. They clearly presented the 3 different regimes observed, where the flame cannot extinguish, extinguishes over a delayed time, and instantly extinguishes. They have the correct qualitative explanation for the instant. They have a decent explanation for the instant extinguishing, where it says it's in the first quarter period. However, the threshold for this instant extinguishing doesn't make sense. It says that it should occur in the first quarter period of the sine wave, and the timescales required do not match at all according to the experimental methods. So I'll discuss this later on. They had an oversimplified theoretical model, which assumes the flame moves like a dam-driven harmonic oscillator, which is incorrect, because the flame should rather move like a normal oscillator, where the sound is moving forward and backwards. There is no damping force that causes it to be damped out like the model. Next, the theory cannot actually predict which method of extinguishing is dominant, despite presenting a lot of equations as to what equations are used to model the flame, using the velocity profile, the paraxial fit, and using even Kelvin-Helmholtz explanation to explain how the paraxial approximation deviates. None of these equations were actually shown how they were solved to show any theory data agreement for the experiments. All they showed was how the frequency of the sound changes with distance, which even though is important as it shows how they characterize their speaker, it does not actually show us what equations they solved to tell us when the sound extinguishes. The problem statement tells us to investigate whether the flame will be extinguished. By using all these equations, if they're unable to explain why it can extinguish or when it can extinguish, it does not actually answer the problem statement. And they've merely taken a lot of data points to explain when it could do it so theoretically. Next, they had a rather poor experimental scope where the sound amplitude needed for extinguishing is not really explained. I would think that increasing the sound amplitude will cause the flame to oscillate further. When it oscillates further, it could be cooled down a lot faster, And because of that, the time taken to extinguish would be shorter, and the threshold to extinguish could be different. However, this is not varied, and I feel that this is a rather important parameter. Next, they only explain that they used one fuel source, which is the ethanol in the Bunsen burner, and that explains how the flame properties are varied. However, I would think that by using a candle as well, you can see a lot more interesting behavior, such as how a candle flame's paraffin wax that's being melted would cause a different range of combustion. And seeing how a different fuel source like a candle or a Bunsen burner, which is different efficiencies, would have different vaporization rates for the different kinds of fuel, would allow us to see different kinds of flames and how they would extinguish. So I think that this is a rather missed out point as well. Overall, I'd like to firstly discuss the qualitative model, then the quantitative, and then the experimental scope. I would now like to invite the reporter up for discussion.
Initially, I would like to explain by saying that the Gaussian profile was used to explain the exponential decay rate of this of the fire, and then through the decibel and the frequency observations, it also increased the energy of the sound wave. Therefore, I do not believe that by varying the amplitude directly is beneficial.
So if that's the case, could you draw for me the amplitude of the sound against the distance? So if this is a speaker over here, then what would the amplitude graph look like?
So the amplitude, of course, would will slowly decay. So for example, sound comes out like this, and the amplitude will slowly decay, as seen in our Gaussian profile model.
Could you go to the Gaussian profile model,
Yes.
please? So do you verify this Gaussian profile specifically? Like, as in, you take a certain point from the distance of the speaker, and you vary the radial distance, and to see if the Gaussian actually is matching.
Sorry, let me find this. So here, as you can see here, the Gaussian profile was proved through to be the solution through the continuity and the Navier-Stokes equation.
I see,
And
okay.
then through this, we also experimentally verified that the flame looks similar to a velocity profile as given here.
I see. I
Similar to
think,
Gaussian
thank you for
profile.
clarifying that first. I think now I'd like to move on to my actual discussion points. So firstly, you said that you wanted to talk about the instant extinguishing, right? Could you
Yes.
reiterate how instant extinguishing works?
Yes, allow me to go back to the slide. As you stated, I think you all have also missed my point on instant extinguishment. As you stated, only the Q cooling exceeds the rate of combustion. However, I also mentioned that it causes, since the wind is very turbulent, it also causes the flame shape to extremely deform, also causing the flame to instantly extinguish.
So what you're saying is that if this is the sine wave of the sound, right?
Yes.
So you're saying that as the flame moves with the sound, the moment it reaches the peak sine of the wave, as in the moment it follows the sound wave and it quickly moves away from the flame, it should extinguish, right?
Yes.
So you're saying that within this time scale, it should extinguish?
Yes, so I'm saying that normally flame, when it's about to extinguish, maybe it will oscillate back and forth. However, this one is only pushed back one time, and it instantly extinguishes. This is also because the burner tip is pushed, the fuel vapor is pushed too far away, so the flame cannot reignite at the burner tip.
I see, thank you. Could you go to your graphs which shows the frequency required for instant extinguishing?
Oh, what? Okay.
You said that for the instant frequency range, for the instant extinguishing range, there are certain phase plots, right, experimentally. So could you maybe right now state what the frequency you used was?
Is it the phase diagram graph?
Yes, so what is the frequency required for instant... so you said over here that the frequency for instant extinguishing is rather high, right?
Yes.
It's at least 95 hertz, right?
Yes.
So if we do an order of magnitude approximation, you're saying that T extinguishing is within this time scale, which is 1/4 frequency, right?
Yes.
So if this is 100, then this means that your time scale is 1/400, which is definitely not less than 0.2, no?
However, the value I gave you is just an approximate, and it's just a range. Lengthened extinguishment is not only at the one value, but however, it's rather a range of values.
So, but I don't think that I'm talking about the instant extinguishing here. You're saying
Yes,
that
okay.
this is the time scale that's actually required for instant extinguishing. But what you've told me is a rather approximation that is less than 0.2, right?
Yes.
So do you have any more accurate approximations for this, like the instant extinguishing?
We have measured the time. However, this was not prioritized during our presentation, for I do believe it is irrelevant to exactly know the time of the instant extinguishment, as it will not help explain the phenomenon.
So, my point is that the point is too big to be seen, and what I'm trying to say is that I don't really think that the instant extinguishing is the correct phenomenon here. The problem statement is sound versus fire, right? It's about the sound oscillating the flame. Why would instant extinguishing even be an important parameter here? Because
Instant extinguishers is just a mere classification of the types of extinguishment as seen in the phenomenon. For there are 3 types: lengthened, known, and instant. So it is not like a parameter we vary.
okay, I think we can agree to disagree on whether your T extinguishing parameter is accurately measured and is qualitatively correct. So I'd like to move on to your theoretical model instead. So I see that you've presented a lot of equations. I'd like to go through your computational flow. So could you go to your first theoretical slide?
My first, pressure profile?
Yes. So if I'm understanding you correctly, is this your computational flow? You solve for the pressure profile of the sound, and then from there, do you model the motion of the wind or the motion
Yes, we modeled the velocity profile of the wind.
of the wind? So you're
Yes.
saying that the pressure, which is a bunch of Gaussian profiles, it causes a wind flow, and that wind causes the sound to extinguish, right? So it causes the flame to extinguish. So you're saying that there's a constant wind flow forward always.
Yes, acoustic streaming is the net flow of air.
I see. Could you go to one of your videos then? Because I see your flame is not constantly moving to the right. It's rather shaking a bit to the left as well.
Yes, however, although there may be a net for a stream of wind, it doesn't mean that the wind is always turbulent enough to always move the flame in one unidirection.
So your flame's actually not always in one direction.
Yes, it is not always in one
So
direction.
you're saying the wind's actually moving left and right.
Yes, so if I were to show this fast Fourier transform of the flame, you can see that, for example, sorry, I'm not sure. Okay, you can see that in this graph, in this graph, you can see,
Just
sorry, can you have the marker, please? So if we perform a fast Fourier transform of this graph, you can see that, for example, this is the amplitude. We can see that the frequency of the flame matches the frequency of the sound, meaning that it also oscillates as well. The flame does not only go in one unidirection, but it also oscillates back and forth, as seen in the fast Fourier transform.
I see.
section.
So I'd just like to clarify something. So you're saying that you solve for the pressure profile as a bunch of Gaussians,
Yes.
and then you find the airflow velocity,
Yes.
and then you solve for the motion of the flame.
Yes.
So before we move on to the airflow of the flame, I'd just like to clarify one more thing. Did you verify this is actually a Gaussian?
Yes, as stated before, it follows a parabolic profile.
Yes, do you have any data points for this?
approximation.
As in radially from this, you measure the data points and you measured whether it's actually a Gaussian profile.
Yes, here.
No, I mean as in if you have a speaker and there's a Gaussian profile here,
Yeah.
that means you're saying that it should form like
so we did test this utilizing the hot wire anemometer, which measures the wind speed. So if we move it, so for example, this is the center of the speaker, correct? So the wind velocity at here would be the most. And then if we move it
I see.
further away, then it would
see.
exponentially
Okay, I
decay.
think I would like to see a graph, but I think we can move on to the next point of your theory.
Also, I would like to go back to the time scale point. That time scale is
Sorry,
not...
I think we can discuss that later. I have
Okay,
a few more
thank
stuff
you,
to discuss.
thank
Sorry. Could you go to your next point about your velocity? I'd like to clarify on what exactly you're solving for here.
The streaming velocity, correct?
Could you go to your previous slide?
Oh, the previous slide.
So, previous slide, please.
Yes.
So you're saying, so you solve for the acoustic intensity and the driving
Yes.
force.
Yes.
So in this case, this force is oscillatory, if I understand it correctly.
Yes.
So you're saying the force will cause it to oscillate back and forth, and this is the velocity
This
from.
is the velocity profile of the flame.
What is UB here?
UB is the boundary condition we set to be 0.
So it's just 0 here.
Yes.
So
So we can just eliminate the first term.
what is mu?
Mu is the viscosity.
How did you measure the viscosity?
Oh, this is just a theoretical prediction.
No,
However,
how did you get that number?
we got that number.
Did you fit it or characterize it?
We got it from the pressure.
I see. I don't see how you got it from the pressure. Could you elaborate
It's
slightly
the
quickly?
relative humidity, which is 40% in this case, and the temperature, which is 28.9.
So it's from literature
Yes,
specifically.
for-
Okay, thank you. So if to explain it quickly, you've just managed to go for. So you just calculate the pressure and then the velocity profile.
Yes.
Could you next go to your temperature? So
My temperature?
after this, please. So you get the velocity profile. Now you go to the temperature. So what you're doing here is, how did you go from the velocity profile to the streaming force specifically?
Okay, wait. Initially, wait. Allow me to show the full derivation in the
Could you explain as you're showing as well?
Okay, yeah, sure. Can you?
As in, do you get it simply from a simple
we get
relation?
get it from simple derivation.
So-
we fully derive for it.
What is some basic equation as I find the slide to just read through?
Okay, so initially through the Okay, as you can see here, through the streaming force, we already know the sound intensity, correct? So through the sound intensity, and this is the linearized Navier-Stokes momentum equation. So after that, we can then find the second modified order pressure, which is solved from the Navier-Stokes equation. And then we can impose boundary conditions, as stated, that UB is a boundary condition which can be set equal to 0. And after that, we can find the actual velocity of the air. Allow me to move on. And then there is the force from the acoustic streaming. And
I
after
see.
that is the
I
streaming-
think there's a bit too many equations. I think, could you simply explain
Yes, yes,
what
yes.
exactly you're doing? Because I'm not
So-
sure how your temperature profile
Okay.
came from the cross-section.
Okay, so let me elaborate. So initially, we want to find the sound intensity, correct? As we model as a Gaussian profile. So first, we want to find the sound intensity equation, and then we utilize this to then find, okay, let me simplify this page. It is basically, we just impose some boundary conditions
I see.
in order
I think-
for this theory to occur.
I
And then
think-
after that, we went through the streaming force, which then we can use to find the streaming profile through
I see. Okay, I think I understand your point now. You're just trying to solve for the streaming
Yeah,
velocity
we-
and then the extinction.
Yes.
Okay, thank you for clarifying that. I'd like to discuss some of the experimental graphs. Could you go to your experimental graphs with your phase plots? So,
the phase diagram.
yeah, phase diagrams. Do you have any theoretical overlay with these?
No, we do not have a theoretical overlay with this. However, I do not believe that is necessary for, we already have solved for the wind streaming velocity.
I see. I
and we
think,
can,
I think even though you've tried to solve it and you have solved it, I think it would be nice to verify that your model is actually
Yes.
correct.
Okay.
Because if you overlay your experiment, your theory, you could see that, okay, maybe your model is correct, or maybe even it's wrong, then we could see some limitations and discuss that. So could you go to your graph, please?
yes.
Uh,
This is the graph now.
I see. Okay. I think I ran out of time.
Okay.
To summarize the discussion, we first clarified the use of a Gaussian profile, which was just to model the velocity profile of the sound. Next, we discussed your qualitative explanation of the instant extinguishing regime, while we agreed that the flame extinguishes in the first quarter period. I mentioned that the time scale for this is orders of magnitude below your experimental observations, so your threshold for the instant extinguishing might be incorrect. We also discussed your computational flow, while I clarified a few assumptions, such as the Gaussian profile, and how you used an anemometer to verify it, although no graphs were provided. We also clarified how the streaming profile on the flame was obtained. We then highlight the... so in summary, I think we've discussed how the reporter goes from the Gaussian profile to the sound wave to the intensity to finally get the streaming velocity. From the streaming velocity, they then manage to calculate whether we instantly extinguish, lengthen, or not extinguish at all. However, there was a complete lack of theory data verification for any of the parameters except for the frequency of the sound. While verifying the frequency of the sound is important, they have not verified anything else. In conclusion, I don't believe the reporter has fully answered the problem statement due to the lack of theory data verification.
Hello, my name is Anna from Team Slovakia, and I would like to ask some questions for the review. So, for the opponent, do you believe that the extinguishment of the flame is caused by oscillatory motion or by a constant acoustic wind?
I think that there are both parameters, there are both mechanisms that are varied, but the explanation for the instant extinguishing is incorrect. But I think that both of them are present.
And which one is more important?
I think that that depends on the frequency range. In this case, I think their oscillatory motion is more important.
Okay, what does the reporter think?
I believe that it is the acoustic streaming from the speaker.
Okay, for the slide 32, yes, or rather the slide where you have the velocities needed to extinguishment.
This?
Yes, this fit right there is your theory
Yes.
for the acoustic streaming.
Oh, this is just a best fit. Like,
So it's fitted.
yeah, it's just fitted.
Okay, so you don't have any theoretical prediction for this.
No, however, we did derive for the acoustic streaming wind velocity.
Okay, and do you really believe that 0.2 meters per second is enough to extinguish a flame?
It is merely just a range, so yes.
Okay, what does the opponent think?
I
Is it
don't-
enough?
I don't think 0.2 seconds in is correct for instant extinguishing, as I've shown by my order of magnitude approximation.
Wait,
Okay.
Sorry, 0.2 second is the milliseconds, no? Or the
Meters per second.
time.
Okay, let's move on. I would like to ask the reporter whether if we had no diaphragm on the speaker, but same sound, would the flame still extinguish?
Sorry, may you please repeat the question?
If you had the same sound, but no diaphragm that is moving, would the flame still extinguish?
If there's wind, then yes. But if there's no
But would there
diaphragm
be?
causing wind, then no.
Okay. Well, do you think that there is also some wind caused by the mechanical movement of the membrane?
Yes.
Okay, and is it the same as the acoustic streaming?
It aids in the acoustic streaming, however, it's not the same.
Okay, and does it have a large effect?
I believe it has not that large of an effect.
Okay. Does the opponent think that the Gaussian experimental proof was sufficient?
They said they verified it, but it would be nice to see some graphs to verify. I don't really think it's a Gaussian. I think it should be in some other form, such as the Kirchhoff-Helmholtz integral, which is the more accurate way to present sound. But if they had verified it and they had showed some graph, I'd been more convinced.
So it was not
It was not
enough.
shown, yeah.
Okay. And then I would once again like to clarify with the reporter, is there any graph where you have comparison between your theory for acoustic streaming with the experiment concerning the air velocity needed to extinguishment?
No, we have not plotted out the acoustic streaming velocity as high various fitting parameters, which would cause the...
Okay, so you have no theoretical predictions whatsoever.
Yes, however, we do have a theoretical graph comparing theory for another experiment, which...
Okay, thank you. Hello, my name is Anna, and I will review the problem number 12 today. So we are already familiar with the problem statement, so let's move on to the reporter. First of all, I would really like to praise the experimental setup that was constructed. I like the use of the thermal camera that made us understand how the heat looks like inside of the flame, and I like that they used gas lamp for more consistent flow of fuel than a candle. However, I think this also could have been varied. I liked the modeling of the flame displacement and that there is some critical value for it to get extinguished, which was really nice. Then they modeled the sound spreading using Gaussian profile, which seems okay. However, I would really like some more thorough experimental proof whether this is applicable. Then I really liked that the explanation that the cause of this effect is the acoustic streaming. And this was, I think, explained really clearly, considering this really unintuitive, complicated phenomenon, which is caused by the nonlinearities due to viscosity. However, what was, I think, a bit of a negative was that she didn't consider the movement of the diaphragm that causes some mechanical wind from the speaker, and thinks that this is actually irrelevant in their case, and it's only the acoustic streaming, and I think this may be the cause why some deviations appeared. we saw no theoretical prediction for the extinguishment of the flame whatsoever, which I think is quite sad, since a lot of time was spent on the quantitative theory, but it was in the end not used. We just got the sound prediction of level of amplitude of the sound over distance, which was not really in contact with the theory, and it's just easier. Then they, for the velocity to airflow, it was just a fit and actually no theory. And I think it was quite suspicious that the velocity that was measured was really low, like 0.2 meters per second is, I think, really small for flame to actually get extinguished. For the opponent, I really liked that he asked a lot of clarifying questions, such as the time of extinguishment, how was the flame defined, and some theoretical predictions for extinguishment. However, I didn't like that he didn't really let the reporter answer on some of the questions. I like that he pointed out the lack of predicative power and no comparison with the quantitative theory whatsoever. And also the poor experimental scope. I think much more with precise setup that was there, more parameters could have been explored, such as different fuel source or different amplitudes of the sound or height of the flame and so on. And I like that he pointed out the experimental setup. However, I think he kind of misunderstood what was the actual cause of extinguishment, since the reporter thought that it was mainly the acoustic streaming, and he mostly focused on the oscillatory motion. For the discussion, I think it was pretty fruitful. First, they discussed the Gaussian profile and the verification to the measurement, and we think and we agree with the opponent that it was not really sufficient. Then they discussed the instant extinguishment of the flame and how it works, and that it's only displaced in one direction. Then they discussed the time scale of the experiments and whether they match or not, and I think there was some misunderstanding whether it was oscillatory or not. Then for the fast Fourier transform, we didn't quite understand, and I don't think it was clarified what exactly was it used for and caused by. Then they discussed the velocity versus streaming force and how was it obtained, and they showed us the throughout derivation, and I think this was really nice to clear it out. Then they discussed the theoretical predictions, and I think that in case of phase diagram it was not really necessary. Thank you for your attention.
So initially, thank you for a great and fruitful discussion. However, initially I would like to clarify the time scale. So the extinguishment time scale is like similar to the thermal time scale, which it takes time to remove the heat, and the time scale that the streaming used to cross the diameter out of the fire. So at first I would like to clear that up. And the Gaussian profile is both quantitatively and qualitatively improved. That, for example, if we put, as I experimented, we put the anemometer at the middle of the speaker, we can see that the sound intensity slowly decays over time. Therefore, I do believe this Gaussian profile is the rightful modeling for this phenomenon. And later, I would like to clarify that through the various discussions with the opponent, I do agree that there should have been, I now do agree that there should have been somewhat theory versus experimental data graph to further clarify this discussion. However, I do disagree with the opponent in various facts such as modeling the Gaussian profile, in which I have proved, and also in terms of the timescale velocity, in which I have stated that the timescale of extinguishment is not exactly the timescale in which you have explained, which I do believe is incorrect. And I would like to reiterate to the reporter that, as stated in the review slides, that fuel vapor was also displaced, as seen in this slide, Therefore, fuel vapor also displaces, as well as the heat, therefore helping to induce extinguishment. Overall, this was a fruitful discussion with the opponent, and I would thank the reviewer for a great reviewing of this problem. Thank you for a fruitful discussion and a nice physics fight.
So, juror questions? And come in.
What is the difference between the theory lines and all of these frequencies? Because it all looks very much the same.
Decibel required to extinguish fire also increases. So here the sound intensity is like similar.
Okay, so it's all the same theoretical lines for the frequency.
Similar, yes.
In fact, while we're on this one, can I just ask you about your decibel scale? You've got 0 decibels. How does that work? And on other ones, you had like 80, 90 decibels, 100 decibels for extinguishing. So oh, it's a change in decibels. It's not sound intensity. It's just labeled sound intensity. It's change in sound intensity. Okay, thank you.
I would like to stay on this slide here. So, but what I can see is that over the distance, it seems to be there is a slight trend that it undergoes your predictive line. What is your biggest distance where you stopped your measurement? So did you go further, or is that the range?
That's the highest distance. So I stopped at 55 centimeters away from the speaker.
Do you have an idea why we have like measurement points that are slightly below to the limit of the distance? Would you have an explanation, a qualitative explanation, why some of the measurement points are lower than the predictive line towards bigger distances?
Oh yes, so it could possibly be like the decaying rate, and also taking into account to real life conditions rather than the experimental theory. We also assume that there is some things, some assumptions that could have caused an overestimate of the.
Question to the reporter first. So when you were deriving the formula for the velocity profile, what were the boundary conditions? You were performing the experiment in the room. Just simply you can say, where was velocity 0?
Okay, so U and B was where the velocity was 0. So the boundary conditions is where the area where the flame comes out. So for if I were to draw.
For sound, I'm speaking speaker, the sound that is coming out of speaker. At what distance was the velocity 0, let's say?
Sorry?
At what distance from the center was the velocity 0, taken 0?
Oh, so it was slowly decay, so at the outer rim of V0.
Of the speaker?
Yeah.
Okay. Can I ask another one?
Yeah.
Question to the reporter. You and also opponent mentioned that Gaussian distribution should have been proved that it was a correct assumption. Can you tell me, first reporter, how could you verify that? A reviewer, my bad, I'm asking reviewer. So you said that Gaussian distribution should have been verified. How could you verify that Gaussian distribution was a good assumption?
I think he should have measured the sound intensity in different distances, like perpendicular or to the speaker. So we
just
could
on one
see,
axis?
on the y-axis, like maybe I can. Yeah.
Do you agree, the opponent?
I think that yes, they could have varied like the radius from the speaker and to calculate what the intensity would be. But I believe that even a Gaussian approximation, there are more accurate methods available, like the Kirchhoff-Helmholtz integral, which accurately models how the sound would decay.
Following up, you mentioned now the diameter of the loudspeaker should also be varied. What else could occur if you do that?
Sorry, where were we?
You now mentioned that you could actually change the diameter of the loudspeaker and see some further effects.
The diameter of the speaker itself, the diaphragm. Yeah. I don't think that's what I meant. I meant that the Gaussian profile is an approximation. That's the easier way. But if on the point of the diameter of the speaker, I would think that with a larger diaphragm, there's a bigger volume of air that's oscillating. So I think that the overall effect of the flame is still the same, just that the diameter won't affect as much.
Can you go one slide back, please? 32. Without the blue, yeah. This might be an issue of like color, but like what does the white region mean? Is this like lengthened?
Region is the lengthened experiment. And for the white regions is regions we did not test.
Okay, the gray points are the two ones in the middle. Okay, yeah, never mind.
Okay, I think we're out of time for the questions. Thank you very much. We will try and give you some nice grades. this on? Yeah. We are now in a position to award our marks for the sound versus fire. So I gave it 7, and we have a 7 and an 8 and a 6 and a 6. Straight on to the opposition. I gave it a 6, and we have an 8 and an 8 and a 7 and a 7. And then finally we have the review, which I gave it an 8 and an 8 and a 9 and a 7 and an 8. Hey, well done everybody, those are great scores. To give you the feedback, we had an 8 for the report from Daniel, I believe. Yep.
In terms of being consistent, as I was fairly high with the first report, and then I thought that report was comparable with the first one, but in terms of experimental approach, so I ended up with that 8. The whole report itself, before anything was discussed, was for me on the level of a 5. And then during the discussion with the opponent, you were very well, like defending yourself. So I also ended up with 1.5. So by the end of the day, I rounded up as well, and I ended up with that 8. So that was basically how I did it.
Thank you. And we had a couple of 6s. Would you like?
So overall, I think this was a nice experimental approach. However, with many points, I had to agree actually with the reviewer, especially at the point where like the theory that was presented in actually quite a lot of detail, which I also appreciated a lot, was then actually not applied one to the experiment. So I gave like very high marks on the general phenomenon explanation because I think it was really great. However, I could then only give like rather low points to theory in comparison between experiment and theory.
And then we've got marks for the opposition. We had a couple of 8s.
So the grades were 2 for quick questions, very good quick questions. Again, 3 for presentation and 2 for discussion. So the idea is that I liked it at all a lot, obviously. But during the discussion, the questions you were asking, sometimes you were not saying your own opinion. So there were few questions which I remembered it because of that. And also, I don't know, discussion was quite good. Overall, the opposition was good. That's why you have 8. Everything else, I wanted to say about reporter that her answers to the question during discussions was very good. Like you got 2.5 out of 3 for me. So, well, I think it is a good opposition, obviously a good grade, good presentation, everything else, yeah.
I gave a 6 for the opposition, so obviously didn't like it quite so much. I didn't feel the questions were great at the beginning. I just gave it 0.8. I thought the question, what is a flame, was a strange clarifying question, because it was sort of possibly going to be a thesis, or either don't we know what a flame is? And then there was this sort of, I didn't feel, I mean, this discussion about the instant was quite strange. And it did seem as though you were applying a theory which she hadn't applied, but you didn't really push her theory. There were various things you could have talked about. And I felt your conduct in the fight was sometimes a little bit aggressive, and your timekeeping wasn't as efficient. So, I gave you 2.5 for speech and 1.5. And then, I took a mark off. I took 0.5 off. Oh, sorry, I'd have to look at my notes to say why. It was definitely a question that came up in the discussion. I think, were we talking about was it frequency that caused it? Sorry. Daniel, you want to add?
Exactly the same partial grades as mentioned before, with my mark. And what I appreciated that you really went through the model, that gave me the chance to see that everything made sense and you can't do more there. Therefore, the reviewer had his focus a little bit more on the theory and how it matches the data, but I like that you went into the model. Thank you very much for that.
Did you give the 9 for the...
Yes.
Yeah, so carry on.
Yes, that's more or less the link now. So when it came to the review, then I found it was very clear. I directly saw in which direction it goes, and you hit all the boxes. I could give you points everywhere, even in the part of missed physics. So I had 2 for the questions, of course, then 2.5 for the review of the report, 1.5 for the review of the position, another 1.5 for the discussion analysis, and then 0.5 for the missed points. So I basically liked how you saw things and that you pointed out that we also have to be aware if something comes across very polished, that there must be some comparison with the theory, with the data points. So thank you for that.
Then we have a 7.
Okay, so for the review, for me, the 2 main issues, for my opinion, was first of all the questions. For me, I would like to be more, to hear more well prioritized questions at the start. The review of the report was good, but I think that the review of the opposition was, I can say, poor. I would like to see more about the review of the opposition. And the discussion analysis was great. And yeah, so for me it was the questions and the review of the opposition.
Everything. That concludes the round. I'd like to congratulate all 3 teams on a really high-quality fight. It's been extremely interesting for me to see how it should have been done. Yep, I've remembered what it was, if you want me to go back over that. So look forward to seeing how you get on. I guess we might see Singapore tomorrow, and any of you close to the top, we'll see. So we'll look forward to seeing what comes out, and congratulations, everybody. To the fight assistants.